We now start module 2 of chapter 3. The title of this module is Analytic Function-I. The concept of analytic function is the heart of complex analysis. Unlike differentiable functions, these functions have many additional properties. Actually, the main aim to study the theory of functions of a complex variable is to learn the study of such properties and behavior of such functions. In this module, we first define analyticity of a function in a given region, and then we define analyticity of the function at a point. We also show that the real valued functions of a complex variable is nowhere differentiable except they are constant valued. The concept of analytic functions gives rise the idea of singular point and also a new type of functions called entire functions. After that, we shall introduce a new type of differential equation known as Cauchy-Riemann equations, and we show that if a function f is differentiable at a point z0, then it satisfies Cauchy-Riemann equation at that point. After that, we provide some example related to this module. Now, we go to our slide. So, we start module 2 analytic functions 1. So, first we define analytic function in a region, then we define analytic function at a point. A complex valued function fz defined in a domain D is said to be analytic in D if fz has a derivative at every point of D. The terms regular and holomorphic are also used with identical meanings in state of analytic. A function fz is said to be analytic at a point z0 if it is analytic in some neighborhood of z0. That is, if there exists a neighborhood of z0 at each point of which fz is differentiable. If fz is not analytic at a point z0, then z0 is called a singular point of fz. Now, remark, real valued functions of complex variable are nowhere analytic unless they are constant valued. As for example, the functions mod z, real z, imaginary z, etc. are nowhere analytic since these are real valued functions but not constant on any domain in the complex plane. The sum, difference and product of analytic functions are also analytic in the same domain. The quotient fz by gz of two analytic functions fz and gz is also analytic in a domain where gz is not equal to 0 in that domain. However, the sum, difference, multiplication of non-analytic functions may be analytic. Now, we prove a result. Let fz be analytic in a domain D such that f of D is subset of another domain D1. If a function g is analytic in the domain D1 and if capital Fz is defined by capital Fz equal to Gf of z, then capital Fz is analytic in D. So, we give proof of this result. Let Z0 be an arbitrary point of D. Then we know a result, that is if f has a derivative at Z0 and if g has a derivative at f of Z0, then the composite function capital F equal to Gf has a derivative at Z0 and capital F dash Z0 is equal to g dash f of Z0 into f dash Z0. By this result, we see that the function capital Fz is differentiable at Z0 and moreover capital F dash Z0 is equal to g dash f of Z0 into f dash Z0. Since Z0 is an arbitrary point in D, it follows that capital Fz is differentiable in D and hence it is analytic in D. Now we give an example. Suppose Fz is a function defined by 1 by z minus 2 and Gz is another function defined by z cube. Then discuss the analyticity of the composite function Gf. So, here the function Fz, that is equal to 1 by z minus 2 is analytic in the domain D, which is equal to complex plane C except the point 2, and Gz is analytic in C. Now, f of D, which is equal to the complex plane C excluding the point 0, which is contained in complex plane C, that is the domain of G. Therefore, d dz of Gf of z, that is equal to g dash of Fz into f dash z, that is equal to 3 by z minus 2 square into minus 1 by z minus 2 square, and that is equal to minus 3 by z minus 2 to the power 4, where z is not equal to 2. Another example, if Fz equal to x square y into y minus ix by x to the power 4 plus y square, if z not equal to 0 and Fz equal to 0, if z equal to 0, then prove that Fz minus F0 by z tends to 0 as z tends to 0 along any straight line, but f dash 0 does not exist. So, suppose that z tending to 0 along any straight line y equal to mx, where m is the slope of that line. Then limit z tending to 0 Fz minus F0 by z, that is equal to, we just put the value of Fz. So, this equal to limit xy tending to 0 0 x square y into y minus ix by x plus iy into x to the power 4 plus y square, and this equal to limit xy tending to 0 0 minus I x square y by x to the power 4 plus y square, and putting y equal to mx, we get this equal to limit x tending to 0 minus I m x to the power cube by x square into x square plus m square, and which gives, after putting x equal to 0, we get this is 0. But along the path y equal to x square, we obtain limit z tending to 0 fz minus f0 by z is equal to limit xy tending to 0 0 minus I x square y by x to the power 4 plus y square, and putting y equal to x square, we get this equal to limit x tending to 0 minus I x to the power 4 by 2 x to the power 4, that is equal to minus I by 2. So, this shows that f dash 0 does not exist, because f dash 0 is equal to 0 if we take the path straight line, but if we take the path parabola, then we get f dash 0 equal to minus I by 2. Therefore, f dash 0 does not exist. So, now we define entire function. A complex function f of z is said to be entire or integral if it is analytic in the entire complex plane. Any polynomial pz, e to the power z, sin z, cos z, etc. are examples of entire functions. It is to be noted that the sum and the product of two or more entire functions are also entire functions. So, now we discuss what is called singular point. If a function fz fails to be analytic at a point z0, but in every neighborhood of z0 there exists at least one point where the function is analytic, then the point z0 is said to be a singular point or singularity of fz. As for example, the function fz given by fz equal to 1 by z is analytic except for z equal to 0, and each deleted neighborhood of z equal to 0, the function fz is analytic. Therefore, by definition of singular point, z equal to 0 is a singular point of fz equal to 1 by z. For the function fz equal to z square plus 2 by z into z minus 1 square into z plus 3, we see that z equal to 0, z equal to 1 and z equal to minus 3 are three singularities of the function fz, because the function is analytic except these points. So far we have discussed the concept of analytic functions, some properties, singular points and entire functions. Now we introduce a special kind of differential equation known as Cauchy-Riemann equations, and we also show that if a function f is differentiable at a point, then it satisfies Cauchy-Riemann equations. We also show that this condition is necessary but not sufficient. That is, if a function f satisfies CR equation, that is Cauchy-Riemann equation, at a point, then the function may not be differentiable at that point. We also provide some example in support of this. Now we go to our next slide. So now we prove a result. Suppose that f of z equal to u xy plus I v xy is differentiable at the point z0 equal to x0 plus I y0. Then the first order partial derivatives of u and v at x0 y0 satisfy the equations u x equal to v y, that is partial derivative of u with respect to x is equal to partial derivative of v with respect to y, and also partial derivative of u with respect to y is equal to minus of partial derivative of v with respect to x. So, given that the function f z is u plus I v is differentiable at z 0, that is equal to x 0 plus I y 0. Therefore, by definition of differentiability, we have f dash z 0 is equal to limit z tending to z 0 f z minus f z 0 by z minus z 0, and that is equal to limit x y tending to x 0 y 0 u x y minus u x 0 y 0 plus I into v x y minus v x 0 y 0 by x minus x 0 plus I into y minus y 0. So, since f dash z 0 exists, 2 must exist for all mode of approach of the point x y to x 0 y 0, and all the limiting values must be same. So, assuming z tending to z 0 along a line parallel to real axis, that is y is equal to y 0 and x tending to x 0, we obtain from equation 2 that f dash z 0 equal to limit x tending to x 0 u x y 0 minus u x 0 y 0 plus I into v x y 0 minus v x 0 y 0 by x minus x 0, and that is equal to limit x tending to x 0 u x y 0 minus u x 0 y 0 by x minus x 0 plus I into limit x tending to x 0 v x y 0 minus v x 0 y 0 by x minus x 0, and this is equal to partial derivative of u with respect to x at the point x 0 y 0 plus I into partial derivative of v with respect to x at the point x 0 y 0. This is equation number 3. Now, we choose another path. So, letting z tending to z 0 along a line parallel to imaginary axis, that is x is x 0 and y tends to y 0, we obtain from equation 2 that f dash z 0 equal to limit y tends to y 0 u x 0 y minus u x 0 y 0 plus I into v x 0 y minus v x 0 y 0 by I into y minus y 0, that is equal to limit y tending to y 0 u x 0 y minus u x 0 y 0 by I into y minus y 0 plus limit y tending to y 0 v x y 0 minus v x 0 y 0 by y minus y 0, and this gives minus I u y at the point x 0 y 0 plus v y at the point x 0 y 0. This is number 4. So, since f dash z 0 exists, 3 and 4 must be identical. So, comparing 3 and 4 and equating the real and imaginary parts, we obtain u x equal to v y and u y equal to minus v x, which is our required result. So, note the equations u x equal to v y and u y equal to minus v x is known as Cauchy-Riemann equations, that is CR equations. the Cauchy-Riemann equations are the necessary conditions for the existence of derivative, but these are not sufficient. In other words, we can say that if fz is differentiable at z0, then the Cauchy-Riemann equations are satisfied at z0, but the converse may not be true. In polar form, the Cauchy-Riemann equations can be written as del u del r is equal to 1 by r del v del theta, and del v del r is equal to minus 1 by r del u del theta. So, now we give a remark. We know that the pair of conjugate complex variable z and conjugate z can be written as x is equal to z plus z bar by 2 and y equal to minus I into z minus z bar by 2. Now, we introduce the following differential operators. Number 1, del del z, which is equal to del del x into del x del z plus del del y into del y del z, and which gives after simple calculation as half into del del x minus I del del y, and another operator del del z bar, that is equal to del del x into del x del z bar plus del del y into del y del z bar, and this will give half del del x plus I del del y. So, if f equal to u plus iv, then we have partial derivative of f with respect to z, that is equal to del f del z, and this is equal to half del f del x minus I into del f del y, and after differentiating we get this equal to half ux plus vy plus I into vx minus uy. Similarly, del f del z bar, that is equal to f z bar, this equal to half del f del x plus I del f del y, and this equal to half ux minus vy plus I into uy plus vx. Therefore, the Cauchy-Riemann equations are exactly equivalent to f z bar at the point z0, that is the partial derivative of f with respect to z conjugate at the point z0 is equal to 0, which is also referred to as the complex form of Cauchy-Riemann equations. With this notation, we have the following alternate form of theorem 2. The result is a necessary condition for a complex valued function f equal to u plus iv to be differentiable at a point z0 is that partial derivative of f with respect to z bar at the point z0 must be 0. The next example shows that the validity of Cauchy-Riemann equations at a point is not sufficient to ensure the existence of the derivative at that point. So, we give example. Let fz equal to x cube minus y cube by x square plus y square plus I into x cube plus y cube by x square plus y square if z not equal to 0, and fz equal to 0 if z is 0. So that though Cauchy-Riemann equations are satisfied at origin, f dash 0 does not exist. So, we know that fz equal to u plus iv. So, here u is x cube minus y cube by x square plus y square if xy not equal to 0 0, and u equal to 0 if xy equal to 0 0, and vxy is equal to x cube plus y cube by x square plus y square provided xy not equal to 0 0, and vxy equal to 0 if xy equal to 0 0. Therefore, the partial derivative of u with respect to x at the point 0 0, that is ux 0 0, is equal to limit x tending to 0 ux 0 minus u 0 0 by x, and this gives limit x tending to 0 x by x, that is equal to 1. Similarly, u y at the point 0 0, this is equal to limit y tending to 0 u 0 y minus u 0 0 by y, that is equal to limit y tending to 0 minus y by y, that is equal to minus 1. Vx 0 0 is equal to 1, Vy 0 0 is equal to 1. So, from this we see that ux equal to Vy and uy equal to minus Vx. Therefore, Cauchy-Riemann equations are satisfied at 0 0. Now, on the line y equal to mx, we have f dash 0, that is derivative of f at the point 0 is equal to limit z tending to 0 fz minus f0 by z, that is equal to limit xy tending to 0 0 x cube minus y cube plus I into x cube plus y by x square plus y square into x plus iy, and that is equal to limit x tending to 0 x cube into 1 minus m cube plus I x cube into 1 plus m cube by x cube 1 plus m square into 1 plus im. Since the value of the limit depends on m and m is arbitrary, we say that f dash 0 does not exist. Now, we give another example. For the function defined by fz equal to root over mod xy, so that the Cauchy-Riemann equations are satisfied at origin, but the function is not differentiable at this point. So, considering fz equal to uxy plus ivxy, we have uxy equal to root over mod xy and vxy equal to 0. We note that the given function fz is identically 0 on the real and imaginary axes. Therefore, it is trivial to see that ux at the point 0 0 is equal to uy at the point 0 0 is equal to vx at the point 0 0 is equal to vy at the point 0 0. As for example, ux 0 0 is equal to limit x tending to 0 ux 0 minus u 0 0 by x, that is equal to limit x tending to 0 0 by x, that is equal to 0. Thus, Cauchy-Riemann equations hold at z equal to 0. However, if we take h equal to r into e to the power I theta, which is not 0, with r tending to 0, we see that limit h tending to 0 f h minus f 0 by h, that is equal to limit r tending to 0 mod r square sin theta cos theta to the power half by r into cos theta plus I sin theta, and this gives e to the power minus I theta into mod sin 2 theta to the power half by root over 2, which clearly depends upon the value of theta. If theta changes, then limiting value changes. From this we can conclude that f is not differentiable at z equal to 0, though f satisfies the Cauchy-Riemann equations at the origin. We give another example. Find the nature of Cauchy-Riemann equations for the function fz equal to mod z square. So, here mod fz equal to mod z square is equal to x square plus y square. Therefore, uxy, that is real part of f, equal to x square plus y square, and vxy, that is imaginary part of fz, is equal to 0. So, differentiating we get ux is 2x, uy is 2y, vx is 0 and vy is 0. Thus, we see that Cauchy-Riemann equations are not satisfied unless x equal to y equal to 0, and hence f dash z does not exist at any point except 0. At the end of this module, we came to know what is called an analytic function and some of its properties. Also, we came to know about singular point, entire functions, and also the necessary condition for differentiability. We also discussed some problem. For more problem, you can see the self-assessment part. You also can see any reference books for more details. This ends module 2 of chapter 3.